Hello, everyone, and welcome to Soil Infiltration 101. What is it, why you need it, and how to measure it? Today's presentation will be about 30 minutes, followed by about 10 minutes of Q&A with our presenter, Dr. Gaylon Campbell, whom I will introduce in just a moment. But before we start, we've got a couple of housekeeping items. First, we want this webinar to be interactive, so we encourage you to submit any and all questions in the questions pane. We'll be keeping track of these for the Q&A session toward the end. And second, if you want us to go back or repeat something you missed, don't worry. We will be sending around a recording of the webinar via email within the next 3 to 5 business days. All right, with all of that out of the way, let's get started. Today, we will be hearing from Dr. Gaylon Campbell, who will discuss how to measure soil hydraulic properties. Dr. Campbell has been a research scientist and engineer at METER for over 20 years, following nearly 30 years on faculty at Washington State University. His first experience with environmental measurement came in the lab of Sterling Taylor at Utah State University, making water potential measurements to understand plant water status. Dr. Campbell is one of the world's foremost authorities on physical measurements in the soil-plant-atmosphere continuum. His book, written with Dr. John Norman on environmental biophysics, provides a critical foundation for anyone interested in understanding the physics of the natural world. He's written 3 books, over 100 refereed journal articles and book chapters, and has several patents. So without further ado, I'll hand it over to Gaylon to get us started.
Hey, thank you, Brad. We probably all had lessons on the hydrologic cycle early in our school careers. We learned about rain entering the soil, being taken up by plants, evaporating into the atmosphere, condensing in clouds, coming down again as rain. The first part of that cycle is the infiltration of water into the soil. And our purpose today is to teach about that process. We'll talk about what it is, why we care about it, how to measure the infiltration and the soil factors that govern it. Infiltration rate is defined as the volume of water entering a unit area of soil surface in unit time. The units in the MKS system are cubic meters per square meter per second. But the square meters divide out the cubic meters, so we could also give the units as meters per second, the depth of water that moves into the soil per unit time. The infiltration rate can be computed as the product of 2 factors. One is the soil's hydraulic conductivity, or its ability, the ability of the soil to transmit water. The second is the force that drives the water flow, and that's a water potential gradient. We use the letter H to indicate the water potential or head. Then we're considering flow in the vertical direction, and the water potential gradient is the derivative with respect to the vertical distance of the water potential. The water potential has 2 components. We call one matrix. It arises due to the adhesive forces of the soil matrix for the water and the cohesive forces within the water. And its magnitude depends on the amount of water in the matrix and on the pore sizes and numbers of pores in the matrix. The other is the gravitational potential. It arises because of the constant acceleration of gravity in the vertical direction. Now, with that much information, we can consider for a moment the process of infiltration and how we expect it to behave over time. We'll represent the infiltration rate with the letter I. That we said was equal to the product of the hydraulic conductivity, K, and the water potential gradient, dH dz. Now we can separate H into 2 parts, the matrix and the gravitational part, H with the subscripts M and G. Now we said that the gravitational potential gradient is a constant. We measure the potential in meters of water. The gravitational potential gradient is just 1. We said that the matrix potential depends on the water content of the matrix. Matrix potential gradients therefore depend on water content gradients. The more water that enters the soil, the smaller those gradients become. So at long times, the gravitational potential gradient becomes the dominant one. If water potential is in meters of water, then the infiltration rate is roughly equal to the hydraulic conductivity at long times. And if you look at the graph on the right, it shows a typical infiltration rate that's rapid at the beginning when the matrix forces are drawing water into the soil, and then slows down toward a constant rate at long times. Now we can and do directly measure infiltration rate, but you can see from what we've talked about so far that a number of factors affect the infiltration rate, and we sometimes want to measure those too. At Meter, we love soil physics, and we love to make instruments. We make instruments to measure each of the factors that we've just been talking about. The Terrace 12 measures water content in the field. The Terrace 21 measures matrix potential. The Terrace 31 is a mini tensiometer for measuring matrix potential very accurately in the laboratory or the field. The WP4C is a dew point potentiometer that measures total water potential of soil all the way from air dry to saturation. The KSAT measures saturated hydraulic conductivity on soil cores that we bring to the lab. The HYPROP measures unsaturated hydraulic conductivity and moisture retention of cores that we bring to the laboratory. The Saturo measures infiltration rate in the field, and it determines the field saturated hydraulic conductivity. All of these measurements relate to infiltration, but today we want to focus on the ones that actually measure hydraulic conductivity. We'll start out then by talking about hydraulic conductivity, the ability of the soil to transmit water. Why do we care about it? Well, it turns out that it affects most of the things that a soil is used for: crop production, irrigation, drainage, hydrology, performance of soils used in landfills, design of stormwater management, soil health. We could go on and on. So if we're doing anything quantitative with soil, we need to know its hydraulic conductivity. The factors that determine the hydraulic conductivity are texture, structure, existence or absence of biopores like wormholes, root channels, compaction, density, water content, and water potential. Well, let's get a little more quantitative and compare hydraulic conductivities we might measure in 3 different soils. We can start by pointing out that the soil can be either saturated or unsaturated, and this strongly affects its ability to conduct water. The x-axis on this graph is the water pressure, or the soil hydraulic head, water potential we've been calling it, and it can be either positive or negative. When it's positive, the soil is said to be saturated. The hydraulic conductivity is a constant, doesn't change with head. When the pressure becomes negative, air can enter some of the soil pores and the soil desaturates. The pressure at which this occurs depends on the size of the largest pores in the soil, and is called the air entry pressure, shown as the H sub E on the x-axis. 3 soils are shown here: a well-structured clay soil, a structureless sandy soil, and a poorly structured clay soil. Well-structured means the clay forms aggregates that contain large numbers of large pores. Since the pore sizes in the aggregates is larger than the pore size in the sand, the saturated conductivity of the structured clay is higher than the hydraulic conductivity in the sand, and the air entry pressure is less negative. The poorly structured clay has the smallest pores, so it has the lowest saturated conductivity and the most negative air entry pressure. Note that the vertical axis is a logarithmic axis, meaning we're incrementing by factors of 10. So the structureless clay conductivity is perhaps hundreds of times lower than that of the sand. As the pressure becomes more negative and air replaces water in the largest pores, the hydraulic conductivity drops, and it drops a lot, perhaps orders of magnitude. Note that the sand with its larger pores drops fastest as pressure decreases, and there's a pressure ahead at which its unsaturated conductivity becomes even lower than that of the clay, even though the saturated conductivity of the sand is higher. Note also that as the pressure decreases, the well-structured clay and the poorly structured clay curves come together. At this point, the pores within the aggregates have all drained, and it's only the pores within the clay itself that are water-filled. So we can easily measure the saturated conductivity of a soil sample. I'll direct your attention to the disassembled KSAT on the right. Samples from the field are collected in cylinders like the one on the right that has the screen over the top of it. The soil core is assembled into the instrument as shown on the left, and a constant and known head of water is applied. Rate of flow is measured, and this, along with the applied head, gives the hydraulic conductivity. We can also measure unsaturated hydraulic conductivity with what we call the high prop. This is a much more difficult measurement, so difficult that few such data existed in the soils literature before the invention of the high prop. Again, a soil core is obtained from the field, brought to the laboratory for measurement. The core is saturated with water and then attached to the high prop base. The base contains two microtentiometers that measure water potential at two depths in the soil core. Now, this assembly is placed on a balance to monitor the rate of evaporation of water from the soil. From a knowledge of the flux of water from the soil in the core and the matrix potentials at two levels in the core, we can compute the unsaturated conductivity. And in this slide, we show a graph of unsaturated conductivity as a function of water content. This is for a Palouse silt loam. The saturation for this soil is around 52%. And if we were to put in the graph the saturated conductivity, it would be several centimeters a day. You can see that by 25% water content, the conductivity is decreased by more than a factor of 1,000. We're down below 0.001 centimeters a day. Now, you can also get the water potential of the soil core from these measurements. And you can use that then to make a moisture release curve. Moisture release curves for soil are a lot more common than unsaturated hydraulic conductivity curves. But to have the kind of resolution that you see in this graph is pretty uncommon. Tensiometers stop working at around minus 100 kilopascals. Then in this graph, we also show this curve being extended with data from the WP4C. I want to talk about measuring infiltration and hydraulic conductivity in the field. We'll start by considering methods that have been used for these measurements and some of the challenges of making good measurements. I'll then talk about the approach we took to design an instrument to make the measurements easier and more accurate, and then show some of our experience with that new device. One of the first methods used for these measurements was the single ring infiltrometer that I've diagrammed here. The ring is pounded into the ground and water is applied. The applied water can be kept at a constant level, and we call that a constant head, or we can let the head decrease with time as water enters the soil, and we'll call that a falling head. Measuring the rate of infiltration in the head at which water infiltrates provides the information needed to compute hydraulic conductivity. Now, as we said earlier, water moves down by gravitational forces, but also moves down and out due to matrix forces. The flow is not one-dimensional. That needs to be taken into account in the analysis. The D and B dimensions are used for those corrections. The double ring infiltrometer was made to provide a buffer of water around the inner cylinder so that the flow from the center cylinder would be one-dimensional. The idea of this is to make the analysis simpler, but of course the experimental part gets a lot more complicated since the water level in two cylinders has to be kept at the same height, while the rate of water loss from the inner cylinder has to be monitored. This is a picture of measurements being made with double ring infiltrometers by Leo Rivera, one of our soil scientists at Meter. He did this for his master's research at Texas A&M University. Leo provided valuable insights to us from his experience there. We undertook the development of the Saturo infiltrometer. Dr. John Norman from the University of Wisconsin also provided important and valuable guidance. Here you see the double rings set up to infiltrate water into the soil. See the water supplies for the infiltrometers. See a pickup and a flatbed trailer for hauling the water, and even the shades for some comfort while collecting the data. Leo made around 200 measurements for his study. Even big infiltrometers like these, though, can have hydraulic conductivities that vary quite a bit from place to place. Each of those measurements took between 90 and 120 minutes. They used over 2,000 liters of water, thus the need for the tank and the flatbed trailer. So, what are some of the things that we might consider based on Leo's master's work and other experience in measuring hydraulic conductivity in the field? So I just said K in the field is spatially variable. We need lots of measurements, so they should be as easy and as fast as possible. The double ring takes a lot of time and water. We used the second ring to make the math easier, but the decision to do that was made before computers were ever invented. That's not relevant anymore. Let's just use math to eliminate the need for the two rings. Possible to simultaneously measure infiltration rate and control head, but it takes a team of two well-coordinated people to do it properly. By doing that electronically, you get a quick return on investment. Finally, and this will make better sense in a few minutes, we need to appropriately account for sorptivity. The matrix-driven flow is part of the infiltration, and I'll show how we automated that. So these were the design goals that we had for the Saturo when we started on it. We wanted to fully automate the measurement and control, wanted to reduce water requirements, wanted to make it portable, make it capable of measuring a wide range of hydraulic conductivities, and we wanted it to do the calculations internally. Even though the calculations are done internally, I wanted to show you how these are done. Dr. John Nemo, a USGS scientist, provided the function we need to take into account the sorptivity and the three-dimensional flow characteristics that result from using a single ring. You can see that by dividing by the function f, whose value depends on ponding depth, infiltrometer insertion depth, infiltrometer radius, and a porous matrix characteristic length, lambda. For these calculations, all but the characteristic length are known. The value of lambda, that characteristic length, is related to the sorptivity that we've been talking about. Its value depends on a number of factors that would be difficult to determine in the field. But if we could alter some condition associated with the infiltrating water and measure its effect on infiltration rate, we could eliminate lambda from the two equations, since it's the same for both. So we change the ponding depth to do that. D1 and D2 are the two ponding depths. I1 and I2 are the infiltration rates that we get for each ponding depth. We show conductivity here as K with subscript Fs. Fs means field saturated. As we infiltrate water in the field, we don't necessarily remove all of the air, so it isn't truly saturated, but that's probably about as close to saturation as we will get under field conditions. Now, we could pump water in and out to adjust the ponding depth, and that's what you do when you're doing this method by hand. And that's why it takes two people. But with the Saturo, we use air pressure. We maintain a constant depth, but raise the air pressure inside the chamber to change the effective ponding depth. In the first graph on the left, you see we maintain an effective ponding depth of a little under 5 centimeters for about 15 minutes. Then we increase it to about 15 centimeters for 15 minutes. Then we go back to the 5 centimeter depth. The graph on the right shows the infiltration response to the ponding depth changes. So averaging over the values circled in red provides the data for calculating hydraulic conductivity. To summarize, here's a diagram of the Saturo infiltration ring and chamber. The black cylinder in the chamber is a sensor that senses water level. Water is added by a stepper motor controlled pump to keep the water level constant and measure the infiltration rate of water into the soil. The chamber is sealed, and the overall ponding depth or water pressure is controlled by controlling the air pressure in the chamber. Here's the whole setup. The chamber's in front. It connects electronically and hydraulically to the control unit on the right, which has the electronic stepper motor, water pump, and air compressor. The water reservoir is behind the control unit. We don't need a flatbed trailer for the Saturo water supply. I'd like to share a few slides showing how a measurement is taken. We start by selecting a location for the measurement and driving the infiltration ring into the soil with a hammer, as I'm showing here. The chamber's then clamped onto the top of the ring and sealed, and the electrical and hydraulic connections are made to the control unit. The measurements are started using the control unit keyboard. Then we just leave it to make the measurements. This shows a typical run. You see a high infiltration rate at the beginning, as we expect because of the matrix forces drawing the water in. It finally levels off after about an hour and a half. The final readings are the ones used for the conductivity calculations. I'd like to end by showing some data we collected in a comparison study we did here at Meter on our soccer field. Here's an aerial shot of the field with the locations of the measurements marked on the photograph we made measurements at each corner and at locations across the middle of the field. We call this pollute silt loam, but it's highly disturbed. Soccer field is near our main building, and all the soil around the buildings were highly disturbed by excavation and backfill, and that affected the readings we get. We made the measurements at each of these locations with a conventional double ring infiltrometer shown on the left and with the Saturo. The table shows a comparison of the measurements. In general, there was pretty good agreement that two locations show much lower conductivity with the double ring than with the Saturo. The two locations are circled in red in the picture. These locations have some of the subsoil fill that's really high in clay. It's subject to cracking as it shrinks and swells. The Saturo apparently was able to access some of those cracks. All the disturbance from installing the double ring may have filled the cracks in. But if we ignore those two measurements, we show reasonable agreement between the two methods. I hope this has given you insight into the methods and options available for measuring infiltration and hydraulic properties of soils. These methods and instruments are now widely used in agronomy, soils, geotechnology, turf, and other fields. As I said earlier, we love soil physics, and we love building instruments that make these measurements more accessible to our clients. We like to think that we make soil physics easier for you. Measurement of infiltration rate and field saturated conductivity are now both easy and accurate. Then they're being used as a tool for assessing suitability of soils for that list of uses that we mentioned earlier. Close to 600 Saturos are now in use making these measurements. Some of the other instruments I mentioned also make saturated and unsaturated conductivity easy to measure. Thank you for being with us today to go through this.
All right. Thank you very much, Gaylon. Okay, so we are going to take some time for questions now. We have, we'll probably take about 10 minutes to take questions from the audience. We do see that there have been some questions that have been submitted. Thank you for those already. There's still plenty of time to submit questions. If you'd like, we'll try to get to as many as we can before we finish. If we do not get to your question, just remember that we do have them recorded, and someone from our Meter Environment team will be able to get back to you to handle your question via the email that you registered with. Okay, so our first question here, let's see. One individual is asking, Gaylon, how does slope impact the field infiltration measurements and instrument setup and interpretation?
Well, that's a good question. We usually look around until we find a nice level place to put the infiltrometer. I don't have a lot of experience making measurements on slopes. Pretty obvious, since we're trying to control water levels and so on, that would be a problem. And so I think the infiltrometer would need to be installed pretty close to level, whether or not the soil was sloping.
All right, okay. Another individual asking, what is the agricultural significance of this data?
Well, as I said earlier, hydraulic properties affect essentially everything that we do with soil, and for soils to be useful in agriculture, the water has to infiltrate the soil and then has to be retained by the soil so that it can be taken up by the plants. We're designing an irrigation system. We need to know how rapidly the water will infiltrate the soil in order to even start with the irrigation system design. If we're concerned about runoff, even in rain-fed agriculture, and the things to do to mitigate runoff, we need to know how fast the water can enter the soil. If we're trying to assess how our soils are changing over time and whether our management practices are affecting our ability to use the soils, we need to know whether the rate at which water enters the soil is changing. So we could spend a long, long time talking about all of those, the individual applications, but it applies in almost everything we do with soils.
All right. This next one is more of a comment and reaction than a question, but if you want to react to this, Gaylon, this person is saying, as an advisor, I try to evaluate which measurement technologies are better suited to field use, unsaturated or saturated infiltrometer devices. I do have old-time double rings and hate them because of the heavy water amount needed. Any response to that, Gaylon?
Well, certainly the unsaturated conductivity is used less frequently than saturated conductivity, but it was exactly that sentiment that led us to make the Saturo.
All right. This next individual, is there any way to address the plant root effect in the field measurement of KS or SWRC?
Yeah, I'm not sure. I mean, decaying roots can leave biopores that can affect conductivity. Yeah, I'm a little stuck on that. There probably are ways, but I haven't thought about that very much.
All right. Maybe we can get back to that individual with more in-depth answers later on. Oh, this is an interesting application. Have you used your equipment in monitoring recovery of burned watersheds, specifically to monitor the degradation of fire-induced hydrophobic soils?
Wow. We have dealt some with trying to measure hydrophobicity with an infiltrometer that I didn't even show here, but we've sold for quite a few years, a mini disc infiltrometer. And I think we still sell those or have them available. But quite a bit of work was done with those exactly in that area. Look at infiltration of water and of alcohol to assess hydrophobicity, and there are a number of papers published on that. We can maybe give you a little bit more information on that in written form.
All right. Okay. How accurate is Saturo measurements as compared to pressure plates and Richards plates measurements?
You know, those are separate things. Actually, it would be probably the high prop measurements that you would compare with the pressure plate, because that's a measure of moisture release or water retention in soil, and the high prop measures that. Again, that's something that we could have and maybe even do have a whole seminar on, but pressure plate is not a very good device for determining moisture release in soil. And so the high prop measurements and the WP4C measurements are much more accurate and useful.
Okay. Let's see. Has the Saturo been used to measure the pre and post development field saturated let me say that again. Has the saturo been used to measure the pre and post development field saturated hydraulic conductivity for land development projects?
I don't know specifically. Dr. Norman, who helped us a lot on the saturo and helped us a lot in getting its design right, had similar projects that he was using a dual head infiltrometer for, and the reason that he liked it so well was that it gave him really good resolution. He was comparing no-till agriculture, as I recall, with conventional tillage, and other methods for measuring hydraulic conductivity. Just the numbers were so variable that he couldn't see the things that he was trying to see with those measurements. And when he started using the dual head infiltrometer, he was finally able to have the resolution he needed to show those differences.
Okay. This next question is asking, are there guides to the recommended infiltration rates for various soil types?
I guess it would depend on the use. Certainly there are guides for that. For irrigated soils, there's a lot about that to tell the kind of irrigation that's suitable for various soils, for use of soils for landfills, say, or for manure lagoons or other applications like that. Again, there are specifications for that. So, yes.
All right. Okay, this next one is asking, is it possible to realize measurements in depth with the saturo, like an aardvark permeameter, to identify the KH of a clade lens, for example?
I'm not familiar with the aardvark. It sounds like that's for measuring hydraulic conductivity at depth in the saturos. You'd have to dig a hole in order to do that. So probably there are other instruments that are better suited to that measurement.
All right. Okay. Looks like we are close to the end. We'll do one more question and then we'll close up here. So this one in general is just saying there's a lot on the news and in discussion recently about soil health. How do soil health and infiltration tie together?
Well, as soils degrade, typically their hydraulic conductivity decreases. And as we do a good job of managing soils, typically the hydraulic conductivity increases again. The soil is not very healthy if all the water runs off of it instead of running into it. And so a number of the saturos that are being used now are used specifically for that purpose of assessing soil health. Again, that's one of the important measurements. I mean, a lot of the measurements, it's easy to go out and take a look and say, oh, that's a healthy soil, or that's not a healthy soil, but it's much more difficult to make a set of measurements that quantitatively defines soil health, and hydraulic conductivity is one of the ways that you can do that.
All right. Thank you very much, Gaylon. That's going to wrap it up for us today. Thank you for joining us. We hope you have enjoyed this discussion. Again, thank you for all of your great questions. As I said earlier, there are several that we did not get to. We do have them recorded, and somebody from our Meter Environment team will be able to get back to you directly to answer your question. Also, please consider answering the short survey that will appear after the webinar is finished, just to let us know what types of webinars you'd like to see in the future. And for more information on what you've seen today, please visit us at metergroup.com. Finally, look for the recording of today's presentation in your email, and stay tuned for future Meter webinars. Thanks again. Stay safe and have a great day.